inherits its own identity. It's a proton transfer. By the proton going, it creates a positive ion where the proton goes, but it leaves a negative ion. The electrons stay on the oxygen. That's why you need to know that concept called electronegativity. I'll fit this in here. Write it out and say it. It'll sink in. Electronegativity. Okay, the electronegativity concept. I'm going to show you the electronegativities of oxygen and hydrogen, how this all comes together. Okay, so what we were saying, if you look at the periodic table here, you're going to find the most electronegative element is up here. The most electropositive is down here. So for all general purposes, cesium is going to have electronegativity value 0.79, so call it 0.8, which is about 1. Okay. Fluorine's 4. So if you have a compound, cesium fluoride, it's going to be the difference between 4 minus 1 is going to equal 3. That's called ionic. The most ionic. Okay, so these values are called Paulings. So fluorine has 4 Paulings, cesium 1. So the difference is 3. Now let's take something like oxygen. Look at our table here. Well, these have different values, so electronegativity is down in this bottom corner. So when we look over here at oxygen, see how it's right next to F? It's going to be really electronegative. Chlorine is kind of electronegative. All these are real electronegative because they want to get that octet. Wanting that one more electron for the halogens makes them real electronegative. So oxygen has an electronegativity of 3.4 Paulings. So for water, see, this is the breaking point here. We got H2O. It's an H to an O bond is what we're talking about here. So what that is oxygen with 3.4 minus 2.2 is going to equal 1.2. So call it about 1. Difference of 1 is called a covalent bond. Fluorine to fluorine is the strongest bond. So watch this here. We took F to F. 4 minus 4 is going to equal 0. So this is the most covalent. This down here. Most covalent bond is F2. Most ionic is cesium fluoride. Down here to up there. Ionic. Here to here. Covalent. So those of you looking for a real explanation on why this is, electronegativity are values of Paulings that measure the pull that an element is going to have for an electron. Like I said, the whole idea of fluorine is that it wants to get that octet. One more electron in there. 4 Paulings, biggest value there is. 3.4 for oxygen, 3.16 for chlorine. So oxygen is even more electronegative than chlorine is. Nitrogen is 3. So chlorine is more electronegative than nitrogen. But These guys now in water, because it's got two other bonds in there, that oxygen is actually able to pull that proton off. So again, a good representation I saw before when I drew this was it looked like a turtle. If you kind of picture the electron pair out of there, you're going to have H plus plus. We kind of call those bonds. We have another electron pair for the 8. The point is, when you get this other electron pair near it, the protons are always pushed together. Where are my balloons here?
Almost cut my hair.
H2O, the hydrogens are real close to it,
Happened just the other
to each
day.
other. And what happens now? You got the water like this. You bring another oxygen up close. It's going to want to pull that hydrogen off. And that's why I said you're left here with the OH. OH is hydroxide. Okay. These guys are still the 104 distance. 104.5 degrees for water, but then it's got the third proton on it. Since it's actually got that electron pair there, it's written as like a bond. The electron pair stays. That's why it gets a negative charge overall. Still got another one over here. So this gets a negative, that gets the positive. So basic OH minus, called hydroxide. Anion. When it's negative, it's an from anode. Right there it is. Positive. Many different names for this, but hydronium. Cation from cathode. Our old joke was, what are dog ions like to chase? Cation. What do cations like? Mouse ions. So this is written H3O plus, and this is the most confusing notation in introductory chemistry because it's really H2O with a P plus. So if you can remember that, you'll get it. This is what water does all by itself. It's called auto-protonization. H3O plus is H2O with a proton. Called it auto-protonization. Again, this is the acid. Okay, so what we say is, use blue here for water, okay? 1 liter
almost
of water
cut my hair.
is 55.5 moles of H2O
Just the other day.
in 1 liter. So as our reference place, 1 liter is it. It's like a pint roughly. So what we take is 55.5.
Said it wasn't my way.
Use our parentheses. Now what that is timesing is a mole, which is the Avogadro's number. So 6.02 times 10 to the 23rd power. That's how many actual water molecules are in there. Now this really works if you learn this, because 1 milliliter of water, which is 1 cubic centimeter, there's all these different names for it, is 1 milliliter, which weighs 1 gram. So it really works out good. Then you take the molar mass of that. 18 milliliters is 1 mole of water, because oxygen is 16 and 2 H's is 1 on average. Okay, water molecules per 1 liter. So it's a big number if you got your calculator, but the 10 to the 23rd is what you look at. So 6 times 50, it's like 300 times 10 to the 23rd water molecules. But what we need to focus in on is the percentage of this liter. There is 0.0000001. Now you see it written as moles, but it's not a whole mole, so it's got to be no S on there. This shows if they know what they're talking about. If they call it moles, it's a fraction of it. 7 places in there. So what I call it is going back to kindergarten. Take this decimal point, okay? Now mole, remember, is the 6.02 times 10 to the 23rd. But we don't want to write all that out, so we just write mole. It's not 1 yet, because we are 1, 2, 3, 4, 5, 6, 7 places to this side. So we can call it 1 times 10 to the minus 7 mole. This is the same thing as that. So what's easier to write? 1 times 10 to the minus 7 or 0.0000? Now this is where I catch the teachers, because, oh, it's minus 7, so it's a small amount. Yeah, well, it's minus 7 times 10 to the 23rd. So you just do the simple subtraction on that. 10 to the 23rd, okay, let's just call it 23 minus 7 is what, 16? So that's the equivalent of 10 to the 16th. Doesn't even matter what the little numbers are. But the 10 to the 16th, that's still a big number, right? 10 to the 16th water molecules in that 1 liter at any given second are as the OH minus or the H3O plus. So this is what's so cool, is water is an acid and it's a base at any given second. Because every molecule that jumped over to protonate a water left a negative OH hydroxide base behind. So they even out, but this happens at any given second out of the 55 times 10 to the 23rd.